Our next talk is by Vladimir Kravtsov from Trieste on Anomalously localized states in one-dimensional.
Okay, thank you very much, first of all, for invitation to this beautiful place, which I like very much, and also now it's so good reason to come. I will be talking about essentially the very old stuff, because it is just one-dimensional Anderson chain. So this is their model of Anderson localization, and still it appears that there are interesting things inside. So this is the subject. First of all, I would like to tell that this work was done in collaboration with Vladimir Kravtsov from Troitsk, Russia, and it was done in ICTP, so International Center for Theoretical Physics. Now, what is it about? So we have just one-dimensional chain of sites on which there is a random uncorrelated energies, which, for example, are distributed according to box distribution, but this is absolutely not essential. Then there is the Schrödinger equation. There is hopping, which is equal to 1. There is a Schrödinger equation with random energy, random on-site energy, and this is the discrete Anderson chain that I'm going to study. So another popular system which was studied in the same context was a continuous one-dimensional model with disorder potential, which, let's say, is Gaussian delta correlated, or maybe a bit more wider correlated. Anyway, so this is the continuous model. So basically, we know that in both models we have Anderson exponential localization at any strength of disorder, but still there is an essential difference between these two models, and this difference is because in this system we don't have a lattice period, so we have a continuous model, and in this system we have a lattice period, and in both systems we have de Broglie wavelength, which is associated with the energy, in this system it is essentially one single length if we have delta correlated potential, so it is one single length which is de Broglie wavelength. And in this system we have two lengths. One is de Broglie wavelength and the other one is the lattice constant, and so there might be commensurability effects, and what I will be talking about is essentially this commensurability effect. So this story is not new, actually. When first computer appeared and people learn how to study localization numerically, almost immediately what was found actually by Angus McKinnon is that if you consider such one-dimensional chain and you compute localization radius, then the localization radius has some strange peak, strange enhancement exactly at the center of the band. So at zero energy in the model which I'm considering. And so it was a puzzle not for long, because next year there was a work by Kapus and Wegner who essentially understood this as a commensurability effect, and they have computed this enhancement of the localization length, although it was some sort of serious expansion for this enhancement. Then there was a very substantial, very long work by Derrida and Gardner. In this work, essentially, it was shown that anomalies like this appear not only at the center of the band at zero energy, but essentially they appear at any point of commensurability of the half of the wavelength and the lattice period. So still the principal anomaly at the center of the band remains the most important one, because in this case the change of the properties, let's say enhancement of the localization length, does not depend on disorder. What happens when you make disorder smaller and smaller, keeping the length of the system larger and larger, then essentially what you observe that the enhancement approaches some constant limit, which is about 10%, by the way, and what is disorder dependent is the width of the perturbed region in the energy space. So it becomes more and more narrow, so that in the limit of vanishing disorder and infinite length of the system, so that the localization radius is still smaller than the length of the system, this is just one point, just one energy. So basically, as I said, this is a commensurability effect, so we have essentially several of such effects. So one, the most simple one is where the wavelength, the half of the wavelength, is equal to the lattice constant, and it corresponds to the band edge. So we know that at that case, localization radius goes to 0, localization becomes strong, and beyond it there is Lifshitz tail. Then there is another extreme where the lattice constant goes to 0, and this is the continuous limit. So all these things not actually reachable in the continuous limit, because in the continuous limit we are dealing only with the bottom of the spectrum, approximating it as parabolic. What I will be considering is where the commensurability is the strongest one, besides the trivial situation at the band center. I mean, trivial in some quotation mark. It is also not so trivial. But so I will concentrate on this case. And what is actually what is the question? Because localization length has been calculated, what remains to be done? To understand what is the question of interest, let us look schematically at the amplitude of the typical wave function and plot it in two different species. One where there is a logarithm of psi squared of the amplitude of the wave function as a function of the distance, and the other time just psi squared in the linear scale. You know, you plot the same thing. What is the difference? The difference is that when you do the logarithmic plot, you blow up the tails. So these tails are absolutely invisible here, and here they are the main thing. But what you skip here is the body of the psi squared, which is well seen here and barely seen there. And so you can, in principle, define two different characteristics which has a meaning of the localization length. One of them is the slope of this logarithmic curve, and this is a very well known Lyapunov exponent. So essentially you study how the localized wave function increases exponentially if you start from the end of the chain. And so this increment is the Lyapunov exponent, which was calculated by all those people before. At the same time, we can define another localization length, which I call intrinsic localization length, which is basically the width of the body of the wave function on the linear plot. And mathematically, it is just inverse the the inverse length is the inverse participation ratio. So it is something which has to do with the average power of psi squared. So the principal difference between these two is the following, that here you do not need to have a normalized wave function. So you do not need even to have an eigenfunction. So you may pick up the energy which is not the eigenenergy, and still you will have exponential behavior with the same increment. Here you absolutely have to have normalized wave function. So you deal with the eigenfunctions. And of course, this is the simplest question where you compute only the second moment of psi squared. But in general, what is interesting is the whole distribution function of the normalized eigenfunctions. And this is what was missing in this theory of the Anderson chain. It was not, I mean, it was known in the continuous model. It was known also in the model of which is described by the nonlinear sigma model, which is essentially many channel model. But it wasn't known in the anomaly where the principal effect of commensurability takes place. So, and this is the main subject of my talk. So I will outline principal objects that I will be studying, and this is also not a new stuff. Essentially, the main framework of how to deal with this problem is taken from, you can find it in the review of Sasha Mirlin and of 2000, and it is based on the work by Mirlin and Fedorov. And essentially, what one needs to do in order to compute the moments, and then having the moments, one can compute the entire distribution function. What one has to do is the following. One has to define so-called generating function, and this generating function is if I want to know the moment at some site, what I have to find a solution for the generating function with the boundary condition on one end, which is this one, and then I have to find the generation function with the boundary condition at the other end, and then meet them together in a bilinear form, and this will be the expression for the moment. What is important in all this business? Basically two things. The most important thing why this generating function is the main object, it is because the generation function is given by a recursive relationship. If you don't have correlation between the disorder on different sides, then essentially you have a recursion relationship where this function at the site m plus 1 is entirely determined by the same function at the site n, and so at all previous sites. But important thing which essentially leads to this commensurating effect is that this function is the function of two arguments, not one. And what are these arguments? So you can say that these are some arguments that appear, for instance, when you do this business in the using the nonlinear sigma model, but you can also derive everything in this one chain, one single chain. You can derive everything in elementary means, and essentially these two arguments have a meaning of the amplitude of the typical wave function and the phase of this wave function. So I can define it more rigorously, but this is the principal thing that that this function depends on the two variables. And so you see what happens. Of course, it is a recursive relationship, but recursive relationship with shifting the phase variable. The phase variable is shifted exactly by the number which is the ratio of half of wavelength and the lattice constant. So this k is pi over 2 for this principle for the center of the band.
Can I ask what the L is again? The L hat.
This is and this is some operator that acts on this function, which it depends on you, and this is in principle it is an integral operator.
Yes.
It is an integral operator, and one can derive it for any strength of disorder.
You haven't put it down yet, or
No, we did.
okay.
No, we did. Not only we. It was done
Yeah, but
earlier.
I mean, have we seen it here?
No, it is not here, but it is done. It was done in earlier works, as a matter of fact. So this is the disorder parameter. When disorder is weak, this is a differential operator in all cases. If I raise it in the exponential, so it will be an integral operator, right? But if disorder is weak, I can expand it, and then it will be a true differential operator. So the origin of the commensurability effect is this shift. So basically, I cannot derive the equation because it was done actually and reported in the meeting 4 years ago. The point is that if I have a recursion relationship like this, I have to close it in order to have the same arguments here and there. How to do it? I have to do as many steps as equal to the denominator of this k, which is if it is pi over 2, so I have to do 2 steps. If it is pi over 3, 3 steps, and so on.
In your first formula giving the mean of psi n to 2m, there is a large n appearing in the left, in the right-hand side in the last term.
You mean these indices?
Yeah, the large
capital N. Capital N is the size of the chain.
Okay, it's the size.
It is the size of the chain, which is considered to be very big but fine.
Okay.
Okay, so now if I know this generating function, then I can compute various things. First of all, I can compute the joint probability distribution of the amplitude and the phase. And this is given since the momentum is given as a bilinear form of this phi, then this guy is also given by a quadratic form. Here, there is an expression which is specifically for k equal to pi over 2. So that's why it is not bilinear but quadratic. So now, then if you know this, you can compute the probability distribution of psi squared just saying that psi squared is u cosine squared of phi. So u is something which is associated with the amplitude of psi. Now, so basically, my goal is to know something about the generating function and then to do all these operations. By the way, this formula, which has a contour integral and so on, you immediately understand why it appears. It appears because there is some factorial, extra factorial here, and so you need to represent this gamma function, which is given by this factorial in an integral form, and so you have this this stuff. Now, now some properties of this generating function. The most important property of this generating function is the following: that if I set the variable u equal to 0, then I have a function of only phi, and this function is known. This is the function which was studied before in the work of Gardner and Derrida and Gardner, and this is the distribution of the phases. So basically what happens when commensurability effects are taken into account is that everything becomes essentially phi dependent. So if you are not in this situation, if you are in the continuous limit, or for weak disorder you are not at zero energy, then this function phi is a function of only one variable, and so when I do this operation I will get a constant. It is a flat distribution of the phases. In this point of the center of the band, this is not the case, and this is the reason for all these anomalies. For instance, if I want to compute the Lyapunov exponent, it is well known for everyone who deals with one-dimensional system. It is well known that if you are not in the center of the band, the Lyapunov exponent is given by disorder squared by 96. So, or the localization length is 96 by W squared. What was the first observation, numerical observation of McKinnon, that it was not 96 but 105 more or less divided by W squared. So all the rest is given by this integral. So it is because this function is not trivial. Now also the anomaly in the density of states. So if you take the density of state divided by the density of states away from zero, but close to zero, you will find some peak in the density of states, which is given also by a number coming from this expression. So this is basically all the old stuff. I mean, I just tell you how to, if I know the entire function, how to obtain all the results known so far. But there are things which essentially require.
Excuse me, I have a question. Can you come back to the previous slide?
Sure.
I mean, the formulas that you wrote are to be understood as a small W expansion, right? That the main first order terms of a small W expansion.
Yes, of course.
Okay.
Of course. I'm concentrated at this case. Also, there are, there are all these integral.
Because for any W, you can.
No. So from now on, I'm considering only weak disorder. Now, oh, sorry. Okay. No, I went other way around. Okay, so, but there are some important characteristics that require the entire function. And one of them is this distribution of psi squared. For obvious reason, because psi squared is somehow associated with u, and if you set u equal to 0, you would not find distribution of psi squared. Okay, so what about the normal situation where these commensurability effects are not taken into account, so where you are not at the center of the band? Then equation for this generating function is essentially very simple. It is like this. And so when you are considering the long chain and you want to have the asymptotic form in a very long chain, so you don't you take this solution independent of phi, because essentially u and phi are separated variables here. You can consider them separately, and so for the energy which is not center of the band at weak disorder, what you have this generating function expressed in terms of the McDonald's function, and this is the old stuff. This is the old stuff. The new stuff is coming now, because when I come to the center of the band, the equation for the same equation, I mean, not the same equation, but the equation for the same generating function will become horrible, because it contains explicitly all these phi's as a coefficient. So what, how I can come from this expression for the previous one? What I have to do, I have to just average over the angle. If I average over the angle, so this term drops, 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 and what I will get the old equation. So our goal essentially was to do something about this equation. What kind of equation we have? We have an equation of the second order differential equation of two variables and of quite a horrible form. I don't know why, but I believed from the very beginning that this problem is nice, and so it should have solution. Maybe for stupidity, I don't know, but sometimes, you know, if you believe, you will find. And so what we found the following, that essentially you see that here the variables u and phi are all entangled, so you cannot do anything about that. But if you do very simple transformation of variables, introduce psi and theta according to cosine squared and sine squared, what you will get a separation of variables. You will get, as a consequence of the previous equation, you will get a Schrödinger equation like this. So this is the zero mode. I'm considering very long chain. So I'm considering only the stationary solution. That I cannot solve the finite chain. I can solve only very long one. Now, what is nice from the very beginning is that when variables separated, the one-dimensional Hamiltonians that appear are extremely nice, because this is, you know, this is the Calogero type Hamiltonians, which are very frequently associated with exactly solvable nice problems. But there is, you know, a lot of burden associated with this Hamiltonian, and the reason is that it is so singular that it's essentially non-Hermitian, because when you want to write down the hermiticity relationship, there is a boundary term which does not go to zero in this case. And that has a consequence, because if you, you know, you can say, well, I have a potential well, and so there should be some discrete spectrum. Not at all. It is not only not discrete, it is complex, because this is not a Hermitian Hamiltonian. This is one of the problems, and this problem tells us that this psi function, even if I know exactly the solution for this one-dimensional problem, and it is given in terms of Whittaker functions, yet the full solution is given by a linear combination of the two. So there is some integral here involved, and an arbitrary coefficient. So how to, I mean, this is, okay, so we separated the variables, but we don't have a solution since we don't know this coefficient. And this is function. This is not just coefficient, this is a function.
Was difference h psi minus h eta or sum?
Sum.
Then why is it arbitrary? It should be zero. You want
I'm looking for this. I'm looking for the zero mode. So one solution should be with the eigenvalue lambda, and the other one with the eigenvalue minus lambda, and that's lambda and minus lambda because of the zero mode. Now,
do you have a boundary condition at the origin or not?
Huh?
Do you impose a boundary condition? What do you do there?
No, the point is that if I have this Calogero type Hamiltonian, I have, I know what is the options for the behavior at the origin. And it is x to 1/4 and x to 3/4. the point is the following, that I cannot actually throw away any of them. I cannot impose the boundary condition like in the in quantum mechanics. So I have to do something else, and this was the main problem because I had to find somehow this function, and this seems to be impossible, but it is possible. So what actually happens is the following, that instead of putting the boundary condition at the origin, which actually is not possible to do, because it is seen that by physics both solutions are good. Now, what one can do is the following. This is the generating function, and I remind you that psi is proportional to cosine phi, and eta is proportional. It is cosine squared of phi, and this is sine squared of phi. Now, what is a natural requirement is that your generating function does not have cusps as a function of phi. So it is actually the function that is pi over 2 periodic and even in the origin. So if you have the natural requirement is that you don't have cusp like this, but you have a smooth function. And it appears that this requirement does the job, because what means it doesn't have cusp? It means the following, that this function does not have branching as a function of psi and eta, because any branching would mean branching of cosine and sine, and that would lead to cusp or to branching singularity. So one can write down the condition. One can write down the condition when this branching path vanishes. Because we know this solution, this is a Whittaker function, and this is also a Whittaker function. And so now it is absolutely important that the solution of this equation is...
Excuse me, I just want to make sure I understand something. If you go back to the previous... okay, no.
This one.
That one. So does that define the Whittaker function in that equation?
This is a Whittaker function, yes. And this is also a Whittaker function, so I will show you now.
Yeah, but I mean, but that isn't a unique solution to that equation, presumably, or is it? It's just a special.
No. The point is the following: that of course, what I require in any case is the behavior at infinity,
yes,
at large u.
So that
fixes the Whittaker function.
Okay.
No, okay, and then you see this is the full solution. This is the full solution. There is a Whittaker function. There is another Whittaker function. And what we managed to do, I have no time now to explain, but this condition of smoothness as a function of phi at the origin, this condition uniquely fixes the coefficient. Now, instead of lambda capital, I wrote lambda small, so there is still an integral over this lambda small, but this guy is absolutely uniquely fixed. So what you see is the following, that there is a solution which involves two Whittaker functions of the index was 1/4, but in some weird way, because the integration variable lambda enters both the argument of the Whittaker function and also one of the indices of it. So this epsilon and epsilon bar is just complex numbers. So that makes this function absolutely difficult to deal with, because if you try to get some asymptotic form available, at least available to me in the literature, you will fail to find out what is this function like. And so the main business that we did now was to find the asymptotics of this solution given by an integral, asymptotics of this solution when u is large. And so when u is large, I can, why it is important? Because since u is associated with psi squared, so if I know the large u asymptotics of the generating function, I will be able to calculate the large psi squared asymptotics of the distribution function. But if I know the distribution of large amplitudes, why the large amplitudes may appear? Because the localization length is anomalously small. So what I'm studying then is so-called anomalously localized state, where the localization radius is much smaller than the typical one. And this is the problem which was once formulated by Dima Khmelnytsky in 95, Khmelnytsky and Muzykansky in general terms. And this is one of the incarnation of it. So basically, the rest of the time is to deal with this Whittaker function and to find the asymptotic form. So the strategy was just to use the integral representation for the Whittaker function, and then do multiple saddle point integrals. For instance, if I do this representation in terms of the auxiliary integration over t, so since there are two such functions, t1 and t2, then after I do saddle point on both saddle point integration on both variables, what I will get, I will get the generating function again as an integral of something which is similar to lambda, because it was a previous integration variables. Now I change it a little bit from lambda to z. But what is important here is that I found by this manipulation a square root behavior of large u here and some action psi plus and psi minus. So now this is a convenient form to go and compute the asymptotic form. And then
So the main saddle point contribution is from just evaluating the Whittaker function with large lambda, or with the lambda parameters in both in front and in the argument.
Yes.
That's where the
That was the obstacle.
That's what the hard.
Yes. And so I just want you to appreciate craziness of this. So this action which stands there is expressed in terms of the elementary function, but you see what kind of things appear here. Yet I can compare the integrand, the exact integrand in terms of Whittaker function computed numerically, and this saddle point approximation of the integrand, and you see what the red curve is inexact for some u and some phi, and the black, which is lying exactly on this, but having a spike here typical of the saddle point approximation, because I have here this denominator, and this denominator gives a spike. But apart from that, the approximation of very complicated function, this is for different phi, here it is not oscillating, here it is oscillating, is very good. So what happens when u goes to infinity is this. This spike for angles like this goes to infinity and gets smaller, and eventually vanishes. And here it goes to the other side of the function. And so the limit where u goes to, where u is very big, actually in this limit this spike disappears. It is integrable anyway. So this is the answer. The answer for the generating function is like this. So it is essentially the exponential of minus square root of u, the same as it was away from the anomaly. The difference is the following. The difference is in the pre-exponential factor. So if you are not at the anomaly, it is u to 1/4, and here it is u to minus 1/4. This is one difference. And the other difference is this function of phi, which will be also important. And so then, okay, I skip this. Why this function of psi is important? Because in order to compute this distribution, I have to do at some point the saddle point integral over the angle, over phi. And when I'm not in the anomaly, when I'm not at the center of the band, then the action in this saddle point integral, it is like this. So, so that the saddle point lies at phi equal to 0, and it is equal to 1. This function of phi that we have computed makes things different. Now the action behaves like this, and the saddle point is shifted to almost pi over 4, and it is smaller than 1. And this is very important. Why? Because when I eventually compute the distribution function, this is the distribution function at the anomaly, and this is the distribution function away from the anomaly, which is known. And you see what happens. So there are two things here. One is that the pre-exponential factor is different. So here it is x to first, x is psi squared. X is psi squared. It is to the first power here and to the third power here. But not only. You have, because of this shift of the saddle point in the phi, and eventually because of the phi dependent function in the generating function, I have here the coefficient which is smaller than 1. And here the coefficient is exactly equal to 1. And you see what happens. There are two tendencies, I'm finishing. There are two competing tendencies. First of all, you have bigger negative power in the denominator, and at large psi, it makes the probability smaller. But at very large psi, this factor which is smaller than 1 compared to the factor that 1 wins, and you have a tendency which is inverted. So basically we have two competing tendencies of what is the probability of very strongly localized state. So if it is strongly localized but not very strongly localized, then at the center of the band it is more difficult to create such state. But when it is very strongly localized, extremely strongly, then it is easier at the center of the band than otherwise. And so this tells you that in this strongly anomalous localized state, there are two different physics which compete. And then lastly, it is the direct numeric diagonalization of the large chain and parameter-free distribution. So it seems to work. And this is the conclusion. The conclusion is basically that we found the asymptotics of the generating function, and this is the comparison with the exact solution, and the two different tendencies in the behavior of anomalously strongly localized state. First, the situation zero energy wins, and then non-zero energy wins. So this is. Oh, thank you.
There are questions. If anyone wants to comment, question or comment?
Question.
During the coffee break. Comments? Then let's thank Vladimir again.